Mukhopadhyay, and other council members of the Structural Geology and Tectonic Studies group for gracing this online platform with their virtual presence. And with the permission of the chair and as your host for today's evening, I'd like to welcome Professor Mallickarjun Joshi to deliver the monthly lecture of this month, organized under the aegis of Structural Geology and Tectonic Studies Group India in association with Department of Geology, Banaras Hindu University. Welcome, sir.
Thank you. Thank
Before
you much. Thank
I
you.
hand over the stage to Professor Joshi, I would like to provide a brief introduction about today's speaker, mainly for our young students and other listeners across India who have also joined us through our YouTube channel. Uh, Professor Mallikarjun Joshi is one of the most accomplished name in the field of metamorphic petrology in India. Though metamorphic petrology is very close to his heart, Dr. Joshi is equally conversant in other fields such as structural geology, tectonics, Himalayan geology, mineralogy, to mention a few. Professor Joshi earned his BSc and master's degrees from Banaras Hindu University. He also did his PhD from BHU under the able mentorship of renowned metamorphic petrologist Professor Ram Swarup Sharma. He started his career as geologist in Geological Survey of India, and he served there from 1980 to 1985. Consequently, he shifted to academia and joined as a lecturer in geology in Humayun University, where he served from 1985 to 1990. Subsequently, he served as reader in Applied Geology Department of Civil Engineering, IIT BHU, from 1990 to 1997. And finally, as professor of geology, Department of Geology, Banaras Hindu University, from 1997 till 2021. He is also the former head of our department and former dean and director, Institute of Science, Banaras Hindu University. A total of 12 PhD students earned their PhDs under his supervision, and he has also handled about a dozen research projects that together amounted to more than rupees 16 crores. He has also published more than 70 research papers in journals of national and international repute and has published a couple of books. He has also having several international collaborations with University of Western Australia, Trinity College Dublin, Queen's University, and British Geological Survey. He was conferred with several prestigious awards like INSA DFG Exchange Award in 1990 and the prestigious National Mineral Award of Government of India in 1994, to name a few. He is also an extremely popular teacher in our department and has also delivered numerous popular lectures in different institutions across India. And also, sir, I consider myself extremely fortunate to have interacted with such a personality over the last few years, and every time he has enlightened me one way or the other. So, without taking much time, I would like to request Professor Joshi to commence his lecture on the North Almora fault conundrum in the Western Himalaya. Sir.
Thank you, Sain. With my gratitude to the Structural Geology and Tectonic Studies group, I express my regards to Professor Dibrugarh, who is not there, to all the council members, and particularly to Sandeep for almost goading into this, and for a very kind introduction, perhaps, which I don't really deserve. This topic is, as you will see, is about some sort of confusion, and as the lecture proceeds, you can see that, well, what I really want to talk about. But essentially speaking, okay, I will try go to the lecture itself because we have lost quite some time. This is the tectonic map of the Himalaya. All of you know about this, but I'll be focusing on this gray area, which is I call as Almora Jajarkot Nepe, which I think is one of the largest nepes in the world. I couldn't find a nepe of this magnitude anywhere else, as far as I know. So we'll be talking about some interesting things of this nepe and about a thrust oblique fault associated with this nepe. Okay, this is the geological map of the area, and This is a regional map, and which obviously has quite some input from me and my co-workers, my students. This green thing is the Ramgarh group at the base, which I demonstrated that it almost encircles. That means it forms the base of the Almora group. So Ramgarh group forms the base of the Almora group. This is these shades of red, you can say. They are the Almora group rocks, metamorphics. Ramgarh group essentially are granite, gneiss, highly miletized. These are the metamorphics, which are included by some later granites of various ages, one of them 506, others 710, and also by a few dikes, which I've dated at about 640. And this all is in the process of being published. And then we have the sedimentaries finally here, which are exposed, and they belong to the Dantha, Tejam, Jonsar, and Masuri groups. We'll be largely focusing our attention to the Almora Nappe and about a confusion or a conundrum that has plagued this area for quite some time. And this controversy has been virtually resolved by force and not with reason. So the attempt is to sort out this conundrum with reason and geological inputs and putting my views further. So this is the fault which I call North Almora fault. This dashed line goes like this. And then this is the North Ramgarh thrust, this dark line. Then this is the North Almora thrust. Then the South Almora thrust and the Ramgarh thrust. So this is what about the Nappe. There are two areas which I have mapped in detail. Of course, I have been working in this area. I have seen done field work in this area, here also. These two areas I have investigated in detail and parts of this area here. Okay, with this much introduction, I go to the this quadrangle. I will show first, and I'll show them something about this quadrangle. Now, in this quadrangle, I show a smaller area to which I go in much greater details. As you can see that here, you have the North Ramgarh thrust. You can see that its sinuous nature is exposed in many areas. So this has got to be a low angle thrust, but it has been normally referred to in geology by very serious workers as a high angle fault. I'll demonstrate that what is the reason for this sort of error. And it is not their mistake, but then, the understanding of things at that level was not there, perhaps in the times when this was mapped. This is the North Almora fault I'll be talking about in some detail. And then you can see that this green thing is the Ramgarh, and this dark brown is the Almora group, which is equivalent to the Munshari group. Now, this is, you can see that these are the triangular fault facets which are developed on the North Almora fault. And show some photographs to give you a feel of the idea. You can see, to appreciate the enormity of this fault, you can see that, I have to go back to this one. All along this line, you see such a rampart of quartzites of the North Almora fault. The details would follow.
Sorry to interrupt, sir. Sir, your presentation has somehow, it is not visible. Actually, it is visible, but in a smaller screen only.
What should I do?
Sir, means it's better you can stop presenting once and then again, means if you could start.
Wait a minute. Okay.
Just means don't log out, simply just stop presenting for some time.
Stop presenting, then?
I think Sandeep,
Sir,
I think without disconnecting, Professor Joshi can go to the slide mode. That was not, it was not in slide mode previously, I think.
Can you see this in now?
We can see it clearly, but then it's better to go, yes.
Yes.
Perfect. I think it's fine, right?
Okay. No, I was in this mode, but I don't know what happened. I just don't know. But so, have you seen this slide earlier, or should I proceed further?
sir,
Yes, I think the problem is not removed. It's still not getting the full screen.
right, sir, right. Sir, actually, it is having only, it is only capturing a small screen. It is coming as a small window.
Any viewer can click on the pin, and
Pin,
on,
right.
on his or her screen, he will see the full screen mode.
Right, right.
Yeah, right, sir, because we can see the full screen.
Right,
My
right,
computer.
right, right, sir.
So should I proceed further?
Yes, sir. Yes, sir. Yes, sir. Please go ahead, sir.
I'm sorry for this glitch. I don't know what happened, but I tried to do anything. I didn't do anything.
No,
Something
sir. It's
happened.
not from your side. It was
Okay.
some problem on our side, I think. Yeah.
Okay.
Please
So,
go ahead, sir. Yeah.
this one, I think this we have discussed. Yes. Can you see this triangular fault faces developed on North Almora fault shrine?
Yes, sir. Yeah.
Okay. So
Yes, sir. Yeah.
this is to give you a physical feel of the enormity of the North Almora fault. And then I'll show you one more photograph to the east of this. And thing continues for a very long distance, almost for close to 220 kilometers. I have seen this in different places that this sort of fault is present. And then it extends further into Nepal and also into Himachal. Now, this again is for a physical feel. This is, as you can see, is a Google map oblique. And you can see that these are the triangular fault facets developed on the North Almora fault. And from the top to the bottom, the measurements I have made, we have gone up to 1200 meters. That is the drop from the tip to the base of this triangular fault facets. Of course, there are a series of fault facets developed during various stages, but from the topmost portion to the river valley, it's close to 1000 meters generally, at places 1200 meters also. So this is a huge thing which needs consideration. And so this is why I'm presenting it to you. Now, the geometry and kinematics of this hitherto ignored crustal scale tectonic discontinuity, that is the North Almora fault, is what we are trying to discuss, because the choice of the tectonic model for response of the Himalayan, South Tibetan and Chambal to the tertiary, or rather Cenozoic Himalayan continental collision, is largely dictated, among others, by the geometry and kinematics of the large origin parallel strike slip faults in the region, and of course by the thrust for their southward movement. So these are the two basic components, and this lecture would essentially address to the strike slip components that have been important in Himalaya, and the much importance has not been given to them in Kumaon Lesser Himalaya. Now, we worked on field, as we have shown you, in the laboratory and the satellite imagery data, and we demonstrated by publishing a paper in 2017 that the North Almora fault and the North Almora thrust is not one, but two tectonic discontinuities. Namely, one is the North Almora fault, that is a steep, south-dipping, high-angle brittle fault with a dominant strike slip and a subordinate dip slip component. And the second is the North Almora thrust, that is the low-angle, south-dipping thrust marking the northern boundary of the large Almora Jajarkot Nepe. Things will become clearer to you as we proceed further. So this more than 500 kilometer long dextral strike slip North Almora fault mimics the approximately 800 kilometer long Karakoram fault, and I feel that it is responsible for significant strain partitioning, just like the Karakoram fault in the west central Lesser Himalaya. This North Almora fault assumes a particular importance, a particular salience for the Himalayan tectonics, because it partitions sizable strains in addition to the Karakoram fault in the region, and lends support to the oblique convergence model that best describes the Himalayan extensional and strike slip deformation. Now, about this confusion or conundrum. Now, majority of the workers, they believe that Almora Nepe is a roughly boat-shaped body, that it rests over a thrust that outcrops at the North Almora thrust, marking its northern limit, as the South Almora thrust marking its southern limits, and they are univocal on this. You have Ganser, Haim and Ganser 39 not listed here, then Ganser 1964, Tiwari and Mehdi, and all these workers, and all of them who are working today are basically referring to these authors and working in this area. However, there has been a group of other workers who sort of receded into anonymity because the thrust tectonics took over and the vertical tectonics people went to the background, and they regard the same tectonic discontinuity as a steep reverse fault, namely the North Almora fault, which was responsible for uplifting the basement metamorphics to shallower levels to juxtapose them with the sedimentaries. And they, you can see that they are people who have been serious workers like Professor R.C. Mishra and R.P. Sharma, Mehdi et al., Saxena and Rao M.N. Saxena, Kumar and Hondial. This is Gopend Kumar, Bhattacharya, 1987. You can't take these people very lightly. And nobody was cheating with the science. They were giving us their observations, but perhaps we thought of sticking to all our own canons and sort of ignored them. Now, irrespective of the sense of movement of the fault, all workers, they believe that the North Almora thrust or fault is a high angle thrust fault. But for I and my co-workers, which we have tried to meticulously demonstrate that the North Almora thrust is not a high angle fault, but it's a low angle over thrust. Why the mistake was there? What was the error? That I would also demonstrate without accusing anybody, because that is something which anybody could have overlooked. Thus, it is not only the thrust fault nature of the North Almora thrust that was in question, but even its angle of dip, whether it is high angle or low angle, was also unsettled. It is puzzling that how competent workers should hold such conflicting opinions on the exact same tectonic discontinuity. And then, admittedly, I thought that both views could not be concurrently right, with a quick caveat that their conclusions cannot be rejected downright either. Now, we examine the problem particularly in the context of such strongly polarized opinions on a crustal scale tectonic discontinuity that runs for over 200 kilometers in Uttarakhand and extends some 300 kilometers collectively to Nepal and in the Himachal. Now, thus the hitherto neglected North Almora fault emerges for me as a very significant brittle fault in the Himalaya, second in importance only to the well-known Trans-Himadri fault, that is STDS. Trans-Himadri was the name given earlier. Now it is known as South Tibetan Detachment System and the main boundary thrust. Unlike the South Tibetan Detachment System or the MBT, North Almora fault cuts across the same tectonostratigraphic units, which is not the case with either STDS or MBTs. The lithologies are the tectonostratigraphic units on either side are different. Now, I actually wrote a paper renaming the North Almora thrust as the North Ramgarh thrust in 1999 in Gondwana research, based on tectonostratigraphic setup that was comparable to the southern flank of the Nape. And because Waldia has identified Ramgarh group on the southern flank, on the northern flank he had identified only the Ramgarh group. Again, none of his fault, because the rocks are so much maltite that they appear almost like schist. When I went to the field, I was always writing them as foliated malnites, which is not a term that doesn't exist in literature. But I think that this deserves a name, because if you go there as a metamorphic petrology, the first impression you pick up a rock, break this malnite, you will think that it is some sort of a schist or a phyllite, depending on where you are picking it, what is the grade of metamorphism in that particular area. So this was the problem. Because of that, none of the earlier workers were able to identify these things as Ramgarh. They identified them as these Ramgarhs in the south appear as myelonites of various types, protomyelonites, ultramyelonites, and normal myelonites. But in the northern margin of the Almora Nape, they are highly they have undergone very intense myelinization, and they have been rendered beyond recognition. And so that was the reason perhaps the earlier workers could not identify them. And also because the understanding of myelites also came later, sometimes in 1980s, that became more prominent part of study. Now, just to give you a regional feel of the whole thing, I'll show you part of the Professor Waldia's map. And this North Almora fault runs all along the northern margin of the Almora Nape. And then the metamorphic rock, they swerve like this, whereas the North Almora fault continues further. We had earthquakes close to Srinagar. Srinagar is should be somewhere here. And then this is always shown as just one line. this is not one line, but there are two tectonic disk countries, and both of them of major regional significance. Now, the smaller part that I took, because I tried to demonstrate, I was interested in studying this damage zone of this North Almora fault, which is a huge brittle fault. And it's at places this damage zone is close to 10 kilometers on the map thickness. As it's a very steeply dipping fault, I think that this fault is nothing less than 8 kilometers or so in the damage zone. This is one of the largest damage zones that you see perhaps anywhere in the world. A huge damage zone, and it has its consequences. So here on this map, this green thing is the Ramgarh group malanites, which have been, these are after the gneisses. The malanites were earlier granite gneisses. They are magnetized. And Almora group is still further south of this, not shown on this map. And then on this diagram, what I want to show you some interesting things. This is with limited lithological input from Chani et al. From geological reports. And then our work is there largely. This dotted thing are the multiplication of low intensity. This I consider that it's a very qualitative sort of appreciation of the whole thing, and the classification is qualitative. But for me, the qualitative thing was like this, that the area which was showing some evidence of brittle deformation, I put it as the beginning of the shearing. There are some zones that it has been started showing some brittle faults, some dislocations that I put in the your low deformation of low brittle deformation zone. This on the margins of this, and the other ones are the places where it has been rendered beyond recognition, where you can't identify anything. That is the high degree of brittle deformation, and then these are the intermediate zones. So this is part of this, and I'll try to again show you that what are these. Again, in different places, the triangular fault facets, so you see them all over the place. They're all over, and this is what I meant by the high degree of deformation. You can't identify anything. It's impossible to measure any dip strike, sort of maybe some relics, but then they're so deformed, so much moved that is only sort of sort of just a chunk is there. I'm still wondering that if these things could be dated, because that would be very interesting and very important. But I'm told by all the experts, and I would like the opinion of the experts on this from all of you, that I have been told that it's very difficult to date brittle fault. But in case you can give me some inputs, I'll be grateful and try that. I have collected some fault gouge, but I'm told that to date the clay from the gouge again is a great challenge. Anyway, let that be. Now, we come to the two dominant features. They can, many number of photographs for them could be shown, but I show you some two of the representative ones. One are the sub-horizontal fault striations in south 80-degree east direction. In this case, with the development of Chatter Marsh, because we are standing on the southern block and beyond, on the other side is the northern block, which is moving eastwards, as you can see from this Chatter Marsh. Where is the cursor? Yes, from this Chatter Marsh. So the movement on like this on this block, and the other way around on the northern block. And then you see conjugate joint sets, which are sub-vertical joint sets are there. And these are localities north of Kafli Gare, that is the place from where this has been taken. This is further north. The locality is some Katpuria is there. Now, the data is very difficult to get because the blocks are highly disturbed. But which blocks I could see that they are relatively better oriented, I collected data from those blocks in the damage zone, and it was the fault striations were plotted, 38 of them. It's very difficult to get them. So, but they plotted. I think the selection was fairly okay of my selection of the relatively lesser moved blocks, and you can see that these are almost sub-horizontal fault striations, so they represent the sub-horizontal movement of the fault. in the roughly east-west direction. And then the conjugate joint sets, the sigma 1 from the conjugate joint sets was plotted. And you can see that they show a very steep movement, 72 degree in north-7 east direction, almost sub-vertical, vertical sort of things. So there are two different movements. One is sub-horizontal and the other is sub-vertical. And both are represented in field. So North Almora fault clearly evidences that there were sizable recent dip-slip activations along the North Almora fault. You can see triangular fault facets. Both the strike slip and the dip slip components are consequence of active movement. Strike slip components are represented by shifting of the Paleo River channels, which I will show you in the diagrams, which are also comprising part of the PhD thesis of Partho. Let me also concede that on this problem, I have been working, this has been very dear to my heart. I've been working on this problem, and I concede that I'm a man with poor wits. I've been working on this problem from 1976. This fault tortured me from 1976, and I could not make head or tail out of it. Today, I am able to make a story and present before you. I have with some sort of satisfaction. So I think you should appreciate my limitations because I was working alone, but was very ably aided by my students, Partho being one of them. And there were a large number of students, difficult to name all of them. So both the strike slip and dip slip components are a consequence of active movements along the fault, but there is no clear-cut field evidence for the relative ages of strike slip and dip slip movements. We can't figure out that which was earlier, which was later, even on a relative scale. So though there is definitive evidence of movement of the fault, both along its strike as well as along its dip, but there is something which is strikingly absent. Every geologist who has read Billings and any book later would always be looking for a oblique movement in the fault which has moved both strike slip and dip slip. But I could not find a single either conjugate joint set that could show me an oblique sort of movement or any oblique fault striations. For me, they are absent. And this I'm saying after trying it for a very, very long period. So the striking absence of any of these oblique striations in the damage zone of the fault suggests that the movements along the strike and dip of the fault were definitely not synchronous and likely appear to have alternated during the evolution of the fault. This also led me to serious difficulties because I was not getting a reference unless I bumped into this reference by Potter et al. 1991, that this can be explained by slight variations in the regional stress field in the recent times that could have produced alternating dip slip and strike slip movements in the weak zone. That Potter describes very nicely in his paper. Now coming to the other area that I showed you that I will be documenting you in greater detail. This is just to show you that this fault takes a swerve. And there is another story which I'll discuss about some time later because this is taking much longer than expected. So this are the rocks of this bluish thing is the Damtha group through which the North Almora fault is moving. Then you have North Ramgarh. This is incidentally a Dwarahat area. And in this area, you can see that then you have the Ramgarh group rocks and the Mylonites have been studied by quad C-axis fabric because they are ductile thrust and they show top to the south movement. So this obviously is a brittle fault and this is a ductile thrust and this is North Ramgarh thrust is ductile. And as you go to the North Almora fault, you similarly get top to south indicators with some of them with changes of sense of reversal phenomena that I have discussed elsewhere. And eventually you come to the roof of the North Almora shear zone, then you have undeformed metamorphics of the Almora group. So this is this part of the story. Then I was talking of the low angle of the North Almora thrust. Now this is a photograph. I have many of them, but I show you two of the representative things. This again is close to the Dwarahat area. And you can see that these are the quartzites, these white colored things and these dark colored things. These quartzites belong to the sedimentaries and these are the Ramgarh group rocks. You can see that the angle is so low. The contact is a low angle contact. This locality is about 1.5 kilometer east of Chowkhutiya, close to the Dwarahat area. And this is close to Kagra area, south of Binsar, for those of you who know, close to Kausani. And here you can see the myelonites above this pencil and the quartzites below this pencil. So myelonites, quartzites, you can put your finger like this pencil is resting on the sharp thrust contact, which is normally not easy in many places in Himalaya. One more photograph, which is about 1 kilometer north of figure B that I showed you and 2.5 kilometer north of Kagra. This shows you that you have quartzites, and then you can see the myelonites lying above this. And for those of you who are interested in seeing some of the ram flat things, well, you will be very much interested in going to this area and studying this further. Now, as I told you that there are, or the people have normally been associating North Almora fault, which some of them were considering as thrust, as a very high angle tectonic discontinuity. Waldia does so, Gansar does so, name the person, everybody is doing like this. This diagram is a part of the diagram and is modified after the diagram I drew in 1999 paper. And this actually shows you, let me sort of familiarize you with this. This is Almora Nape. All of the people have shown this as going something like this, digging into the earth. But I always was thinking that it is very difficult to dig them down and then fold them, and then all sorts of stories will have to be made. But when I found actual low angle contact, and at many places, a sinuous outcrop by strike mapping, I see no reason that why I should consider this as a high angle fault. Like normal thrust, as they are expected, it is a low angle thrust. So this I call as the North Ramgarh thrust, because the contact is with the sedimentary rocks. This is resting. And these rocks, I was telling you, are so highly maltized, and then they are folded because of the later movements. The malnites are folded, obviously, during the Himalayan orogeny or during the movement of this nape, and they are folded into a tight folds or even sometimes isoclinal folds, as you can see. Now, when these earlier geologists were going and taking a traverse, obviously what a geologist will map, will take the deepest point, and these are high angle. How do you blame them? And all this geometry and things, these were not available. I just like to show you just two things. This is not for, this is the upthrown block, this is the downthrown block. This is arrow coming towards you, this is arrow going away from you. So this is the sense of movement for this brittle North Almora fault. And then there are all half bars, those show all sorts of Cenozoic movements. Here there are so many of them. Inside, then Professor Waldia has written many papers on the new tectonic movements within the Almora Nape. These are also part of the same story, of course, interpreted in a different way. Now then, these are the, I'll not waste your time on this. These are the indicators of those ductile, these things. Just one important thing here is that if you see carefully, most of the times the fibers which are expected here are recrystallized. And I attribute this to the last phase shear hitting, because it was such a huge belt that was, a huge ensemble of whole Ramgarh and Almora Nape that was moving like this. So you can expect this type of shear heating. I have tried some thermobarometry using this, and we get temperature close to 400, 450 degrees Celsius for the minerals crystallized within the pressure shadow zones. There have been the recrystallized minerals we have tried. Okay, these again, their acid shear bands show again top to south movements. At places they are reversed because of some problem. This I was referring to you. This strike slip movement is shown very clearly by, you have seen one paleo channel here and the paleo channel here. The shifting is about 2.26 kilometers, and this has been done by Parthu Ghosh. Location is Ranman, where I have also seen this area in some detail. Now, this is a diagram that we drew for eastward extrusion of Tibet along with dextral movement along the Karakoram Giali fault. This is after a surge. And from this area, what we did, Partho and I, that we do all the lineament in this area of the whole of the Almora Nape, and we found this pattern. And we are very confused that, well, how we interpret them, because this would require east-west forces to explain, because this is a conjugate joint set. Till I bumped into another paper by Yin 2010, who explained that the sigma 1 should be in this orientation with maximum effective movement criterion for large scale strike slip faults undergoing lateral extrusion. So this also fell into the slot, and our interpretation was again that this was in response to north-south this thing, but then both the movement are going on there. This lineaments essentially picked up. The last ones are perhaps north-south that we could pick. Now, relating this with the earthquake activity, these are the three thrust all over the place. This Baynard thrust, Munshari main central thrust, etc., with that vector thrust and so on. What you see carefully is this: you have micro seismicity below this fault, below this North Almora fault. They related to the North Almora thrust. We suggest that the North Almora thrust marked in the diagram cannot be seismically active. I'll elaborate the regions, and that the earthquake foci at superficial levels could only be, what we mean by superficial is about 20 kilometers, be related to North Almora fault, which is located immediately below this arrow as we are showing, and is north of North Almora thrust in the section. And they cannot be related to the main Himalaya thrust at deeper levels, which affects the regions close to 25-30 kilometers or so. So this microseismicity, I am inclined to look sort of related to the North Almora fault. So I show the diagram by Hajarika et al. Geophysical Journal International, where you can see that this is South Almora thrust, North Almora thrust, and it's close to 20 kilometers is your main Himalayan thrust. So above what all foci we have, about 20 kilometers, like you see here, this is about 20 kilometers. All these, there is no other major tectonic discontinuity but for the North Almora fault that could be related to this. So this is one of our conclusions. There are enormous seismic implications of the brittle crossing this wide brittle shear zone, which the width is close to 10 kilometers. And most of the earthquakes in Himalaya originate close to main central thrust. And the fault gouge is generally known to reduce the seismic velocity by 30 to 40% compared to the protolith. And you have seen that it is just a jumble of rocks, is almost converted to a conglomerate sort of thing. This is highly likely to reduce the seismic velocity. And this was suggested by Mooney and Gisberg in 1986, that the seismic velocity may be highly reduced, almost to half in some cases. Though there have been some devastating earthquakes like the 1803 earthquake in the Garhwal Himalaya that devastated the town of Srinagar, located almost on the North Almora fault, that is reported by Rajendra and Rajendran 2005. But, and this is the but with capital B, interestingly, there are no historical records of any major damage by earthquakes in Almora region, nor there is any folklore about the damage caused by any past earthquakes in the Almora town that has its beginnings in the mid-16th century. That means almost now we are gone to 21st century. You have close to 17th, 18th, 19th, 30 years. This is not there. We don't have reference of any major earthquake in this part in last few centuries, neither in folklore nor in the travel writings. This was communicated to me by Professor Shekhar Pathak, the noted historian who is also a Padma Shri. He said that, well, we have no record of Kumaon. None of the gazetteers, Britishers, were very profoundly recording whatever is happening, even minor details they were recording. So an earthquake cannot skip their attention. So evidence for an earthquake that did minor damage in the Almora Nape relates to the last major earthquake between CE 1119, 12, 92 in the central Himalaya, was again recorded by Rajendra Rajan, who worked on Seismicity. Now, studies by these authors that included several 7th and 12th century temples and monuments that were older than 1500 CE in the central Himalaya did not identify effects of any significant shaking that could be related to any great earthquake in the central Himalaya during the medieval period in the Almora region. You see, the Jageshwar temple is close to Almora, and this was built in 12th century AD, or now become CE. This has sustained only very minor damage. It's all lies intact. Some people believe that this is one of the Jyotirlings because this is one of the Jyotirlings should be close to Daruka Vane, and Daruka is Devdar, and there is no Devdar in Dwarka in Gujarat. So this is the real thing. There are a number of temples, but that is a different story. So most of the large earthquakes in the Kumaon Himalaya occur close to the main central thrust. Now, it is reasonable to assume that paucity of any evidence of significant historical damage to structures in the Almora Nape in general and Almora area in particular may suggest a role of seismic attenuation. I'll just take 30 seconds here to give you one of my personal experiences. When this Gorkha earthquake occurred, it was felt in all places. It was felt in Delhi. It was felt in Rajasthan by people. But I talked to people in Nainital and Almora. None of them reported that they have felt the Gorkha earthquakes. So this was my gut feeling is this, that this tectonic discontinuity needs to be seriously studied for the seismic attenuation, and maybe this has to be taken into account for deciding about the severity of the earthquake threat in this region. However, the earthquake that destroyed things in Himalaya, there's the Srinagar earthquake in 1803 in the Garhwal region, to which sizable damage in the adjacent areas has been attributed. The North Almora passes immediately north of Srinagar. So, and that is why this recorded damage, because this could have been one of a major fault earthquakes due to the North Almora fault itself. So, and the records of damage suggest that it should have been a shallow earthquake. There is no tectonic discontinuity that can cause a shallow earthquake in this region. Apart from, if you look at the paper of Narula and Shom, 1992, their figure 1, in their figure, one of the locations of instrumentally recorded contemporary adjustments also fall on the North Almora fault west of Srinagar. So the North Almora fault appears likely responsible for both these earthquakes. The epicenter location within the North Almora fault would reduce the distance to be crossed through the damage zone, decreasing the seismic attenuation. Pathak et al. Suggested an asperity parallel to North Almora thrust oblique that we call fault in the northeastern Kumaon region, and that this area is relatively more hazardous seismically. For me, it is prima facie a foregone conclusion that the North Almora thrust, owing to its thrust nature, and this thrust is truncated from its root zone, is a ductile thrust underlying the superficial capping of the Rangwa Almora and Sabal, has no likely role in any seismic activity. It cannot have a role. It is just a superficial capping. However, what Pathak et al. 2015 picked up as North Almora thrust is highly likely to be what we have called a North Almora fault. Their section also shows shallow earthquake foci along the North Almora fault. Thus, there is reasonable evidence of earthquake activity along the North Almora fault, corroborating the field evidence of its active nature, and which also fits in line with this huge fault. The fault running to excess of 500 kilometers, close to 500 kilometers, with a damage zone of 10 kilometer width, which is still active, will create some earthquakes. Now, this is sort of going to summary of the results. I'll give you a physical feeling. This is the upthrown block. Is again a Google oblique, but now this time it is annotated. This is not. You can see some of the Himalayan peaks here. This is Panchachuli for those who recognize this peak. So the Google imagery of the area near around Karanichina, near the head of the arrow marking the North Ramgarh thrust. So this is the North Ramgarh thrust. This sinuous line is the North Ramgarh thrust. Earlier people used to call it NAT, so I called it the old NAT. This red line is the North Almora fault running all along this valley at the base of the triangular fault facets, the sense of movement, eastward movement, and this is the upthrown block. Now, this is a diagram that we published in 2017, and this largely banks on Styron et al. 2011, and who demonstrated that the compression, north-south compression, could be resolved into sort of movements like this. So on this side towards east, on the western side towards west. So these are the western movements, and North Almora fault is adjusting the rocks by moving to the eastern side, mimicking the Karakoram fault here. So you can't believe that the whole ensemble is being moved eastwards and no eastward movements are happening in this area. You have movements in Nepal, TFDS, they are names of the small faults all along, and you see that these things are happening. And this is by and large, the large movement as the whole thing is being extruded because of the compression from the south. So this is, and there, this North Almora fault fits in very well, explaining the adjustments and accommodating the stresses. These are the names of those minor faults. Now, summarizing everything. So debate over the North Almora thrust, all these authors on one side, other senior authors on the other side, is resolved by all the previous workers by conveniently describing this crucial tectonic discontinuity as either NAT or as NAF, depending on their within inverted comma field evidence, ignoring the inconvenient point of view without examining evidence to the contrary. This is what all of us do. We should not blame anybody for this. I tried to look into the problem a bit more closely and found that both of them are right in some ways, and then we have some contribution to the science. Now, Joshi et al. 2017 looked into the problem more closely following Joshi 1999, who had suggested that there could be two very closely running faults, one brittle and the other ductile, that likely led to the disagreement among the previous workers. As I have documented before you, there are indeed two parallel tectonic discontinuities, one brittle and the other ductile. Northern side is the upthrown block. The direction of movement along the strike of the North Almora fault showed dextral movement of the northern block. The base of the Almora Nepe, comprising maltized Ramgarh gneisses, are exposed south of the low angle sinuous outcrop of the North Ramgarh thrust, which is termed North Almora fault by earlier workers. All earlier workers call this North Almora fault. Now, plate motion of the Indian vis-a-vis Tibetan plate can be resolved into an arc normal component shown by orange arrows in the previous diagram, and an arc parallel component, blue arrows, responsible for the arc parallel extension and translation of the origin by Styron et al. The brittle North Almora fault is a high angle fault of regional dimensions that shows large strike slip as well as large dip slip movements, and at places has a damage zone approximating 10 kilometers on map scale. Dip slip movements exceeding 1 kilometer are deduced on the basis of steep, at places 1.2 kilometers, fault scarp with triangular fault facets, while the strike slip movements of the at least 2.26 kilometers are deduced on the basis of shifting of the river channels across the North Almora fault. The northern block of this 502 meter long dextral strike slip, the North Almora fault, which runs all across the Kumaon Himalaya and extends into the Himachal Pradesh in the west and western Nepal in the east, shows evidence of dextral eastward movement. North Almora fault is broadly oriented northwest southeast to west northwest east southeast, and the lineament pattern in the region also appears to have developed with a broad V of the lineament intersection roughly parallel to the regional Himalayan stress, something that was explained by maximum effective movement, as I explained earlier, and undergoing late extrusion as the broad collisional stresses in the Himalaya are oriented broadly north-northeast, south-southwest. And then on a regional scale, the North Almora fault broadly mimics the Karakoram fault and is responsible for sizable strain partitioning within the western Lesser Himalaya, in addition to the major strain being partitioned through the Karakoram fault. The present findings lend additional support to the oblique convergence model of Styron et al. 2011 for the tectonic response of the Himalayan South Tibetan ensemble to the still continuing Cenozoic Himalayan collision. Thanks for your time. That's about all. And thank you very much for giving me this opportunity. I'm grateful to all of you for your time and giving me this opportunity.
Thank you, sir, very much.
Can I remove this now? Any questions?
Yeah, I would like to invite Professor Nivin Mandal for his comments or any queries he might have.
No, this is really splendid talk by Professor Joshi. I have been to this place, but after listening to Professor Joshi's deliberation, I can now understand the tectonic setting there. I have a little questions to Professor Joshi.
Sure.
Do you have any time constraint for the two fault system? One is in NAF and NAT. Are they synchronous or they have a time separation, at least initiation timing?
Professor Mandal, it's an extremely difficult question I am trying to answer, but I have only one clue. And this clue is this, that the North Almora fault is still active. So the activity is still later. When it was initiated, I don't know how it can be.
Okay.
But as it is likely partitioning the Himalayan movements, so it is likely to be a Himalayan fault again. But then I'm sure that you are aware of the work by Professor Dr. Dubey of RDS II Himalayan Geology. And then he's talking about the pre-Himalayan tectonic discontinuities. It is not impossible that there was a smaller discontinuity that got reactivated. But absolutely, I'm clueless on this. But to answer only one thing, that the North Almora fault is still active, whereas the North Ramgarh thrust and North Almora fault, on their margins they are dead. But Almora Nape is being uplifted. So we have new territory. They are being uplifted, but there is no other movement apart.
So there is no seismicity associated with normal North Almora thrust.
How it can be there? Because this is a superficial capping. It is a thrust which is truncated
as you have shown that most of the seismic foci are associated with North Almora fault, NAF, which is strike slip in nature. On the other hand, there are somewhat less seismicity associated with North Almora thrust. So should I assume that the North Almora thrust are aseismic, whereas North Almora fault is seismic?
I think for all practical purposes, there will be movement in the North Almora thrust also, because of the uplift and the adjustments of the that boat-shaped body, and which are occurring, no doubt. But we have not seen, we have no evidence of any shallow seismicity in this area. Okay. This Almora Nape is a very shallow capping. Like if you go to the Almora region and go to the deepest valleys, you will start getting the myelonites again that I associate with the deepest part of the Almora region. This, at least I can relate them to the larger regional picture. So Almora Nape is a shallow body, and this also is sustained by many other lines of evidence. Like there is a 503 plus minus 0.0 or something million-year-old granite body which is intruded it has left an Andalusite imprint in the contact metamorphic rocks. So Andalusites are preserved, chloritoids are present. So in the contact orogen. So that means even at the time of 500 million years, this body was very shallow, less than 12 kilometers or so. So this is a very relatively shallow body. And all field evidence suggests that it is a shallow body. It's not a very deep body. And obviously truncated from because as all of us know, it traveled from main central source to this place. The areas in between are eroded. So from where the force would be applied, it has no connection with its root zone. And it's a body which is essentially moved horizontally.
Thank you, Professor Joshi.
Thank you for your interest, Professor Mandal.
Joshi sir, Abhinav Roy sir has a question, I think.
Hi, sir. Namaste.
Namaskar, Professor Joshi. Thank you very much for the very illuminating talk. Of course, it is not a query, just little clarification I just wanted to learn. That is one of the, as Professor Mondal also raised the point, that they may be two different times, because one kinematic is thrust related, other is the normal faulting. The normal faulting possibly postdating the main thrusting event, because that is a gravitational collapse, perhaps that is the thing. And that's why that could be more aseismic than the Almora thrust, which may be seismic, one point. Secondly, you are using sometimes the brittle fault. Sometimes you are calling that is a ductile thrusting. Okay, ductile thrusting we all appreciate and we understand. But a brittle fault is a brittle. It can, the cataclysite flow can be associated with the fault because the fault is a movement. So this terminology sometimes it is I think should be standardized.
Whenever I am referring to thrust, I am referring to a ductile shear zone, that is the North Ramgarh thrust or the North Almora thrust.
Right.
I never refer to the brittle zone as a thrust. No.
Right. Because they may indicate the different level of emplacement. Because Mallickarjun you are finding, and Mallickarjun certainly is a ductile phenomenon that cannot form at the upper part of the crust. That's the point.
This is, you have got it absolutely right. This is what it is.
Yeah. Right.
This is exactly what it is.
And one more point I may add up, this is, that you have shown these striations, and you have taken then the striation as the really direction of transport. I think we should be extremely careful, because you may find in a ductile shear zones, it is often found that the lineation shows all kinds of variation. They may not directly indicate the direction of movement. So we have to see it is a transmissional shear zones, or it is a monoclinic or triclinic transmissions, because we are always accepting the model is a simple shear. So that's the problem sometimes. So this is not contesting. I'm just only suggesting.
I'll just interrupt you. Your point is very valid, but these striations are from the brittle faults.
Okay, good. Thank you very much.
Any other queries from any other students? Alokji, you'd like to comment anything? Alok sir? Sir, there are no other queries, but I have a few questions because I've been interacting with you on this for quite long.
Yes.
Sir, what is the possibility of considering the brittle fault as a splay of the ductile one? Is there any possibility of?
I for one don't see a possibility. There are brittle faults, splays of the ductile faults, but within the Almora Nape, that's a different story. Your point is valid. They are there.
Okay.
Because all ductile faults eventually, as they come to the surface, they become brittle, and that you can
Right,
see.
right.
They are there. So many of them. Their orientation changes, and the ductile faults at the bottom may show you a almost subvertical brittle sort of uh, portrayal or representation or disposition. Choose the word of your choice, whatever you want.
Okay. So that was the first thing. The second question is that, sir, you mentioned that the brittle fault damage zone is around 10 kilometer thick in map
Yes,
view.
yes,
Sir,
yes.
what the ductile thrust? Is it also of same
Ductile,
thickness or relatively lesser?
ductile thrust is, well, I'll just measure it for you if you give me time.
Yeah.
The map is there, no issues. This is the map. So this ductile shear zone is to close to 4 or 5 kilometers. This is the roof of the shear zone. This is the
Okay.
base.
Okay.
So this will be 2, 4, 5. But this is wider at places. If the myelites are sort of ultramyelites, then the zone are thinner. But if they are protomyelites or ordinary myelites, then this becomes thicker. That is my observation in this area.
Okay. Okay. And sir, the last query is that when, sir, we are looking at an overthrust, then generally it seems that means in case of overthrust, the transport is very high.
Yes, yes.
So in this case, whether the transport is high or low, because I think it is only constrained in this part, or
No,
it
no,
has
no. This
transported to the sub Himalayas as well.
no,
That
no.
I want to know whether we get any
Right.
signature of the same fault in the frontal part as well.
I'll let you know. This is a very
Yeah.
interesting question, and this is a very sort of critical question also. This thrust is a remnant of a huge thrust which once covered almost the whole of the lesser Himalaya.
Okay.
This
Okay.
moved from the main central thrust, and
Mhm.
after erosion, these are the relicts. That is the reason, because these are the relicts. They have no connection with their root zone, and that's why they cannot be seismic. How can you associate seismicity to a thrust which is truncated from its root zone?
Right. Right.
It's a superficial body. It cannot
Mhm.
have any addition. So that is the reason that I associate I am inclined to associate all
Yeah.
the microseismicity with the northern mode of,
Okay, sir.
which is a brittle fault.
Right. Right, sir. Right. Right.
And
Okay.
Professor Joshi, what is the focal mechanism solution for that? Is it consistent with what you are predicting for the kinematics of North Almora fault?
I am yet to see. There people have been working on this microseismicity. I have not seen any. I have been, in fact, desperately looking for those focal mechanism solutions, but I'm yet to find one in any of the published papers. I would be really curious for that. But as yet, I have not seen for this fault. There are focal the solutions for main central thrust, so many of them, or also from the main Himalayan thrust, but for not this for this North Almora fault. Perhaps they are not interested in microseismicity. They're interested in larger earthquakes. Maybe that is one of the reasons. I don't know. Talk to some of the earthquake people that if they can do it for us.
Okay. Microseismicity means what kind of magnitude are you referring to?
They are normally less than 3-4 kilometers. They have some magnitude. I have forgotten exactly what it is.
But I know the seismologists, especially in the frontal part, they are extensively working on the microseismicity and their focal mechanism solutions, because frontal tectonics is nowadays a very interesting aspect for many people, for many geophysicists also. So I think the data should be available for that. Like 4 or 5 seismicity is of interest.
5 perhaps is not taken as microseismicity.
No, less than 5, but if it is a active zone, it can go up to 5. For example,
It can.
if you look at the seismicity, even far in our state, in Birbhum, in a unconsolidated middle, the seismicity goes to that extent.
It does. It does. No, but they're available for the frontal part. This is in the central Himalaya.
No, I know.
So I would be really looking for this, and maybe if I can make any of them interested in this, because by this publication, I just want to draw attention of people to this fault zone. That is one of the major points, that this is a neglected tectonic discontinuity. People should come and work on this. That is.
No, my point was that in order to, I appreciate your interpretation that the geological proxies indicate the fault of strike slip kinematics,
Yes.
but that need to be supported by the focal mechanism solution, if you claim so.
Yes, if I come across some of them, I'll be talking to the people, Pathak, etc., who are working on this.
Yeah.
Who are interested in North fault, that if they can do it for us.
Okay. Thank you, Professor.
Thank you very much. Thanks for interest. Thank you.
Is there any other query from any students? No, sir, I think there are no more queries from the participants here. Yeah. So
thank you.
Thank you, sir, for giving us your valuable time.
Thank you very much for the opportunity and giving me time to share my thoughts.
Sir.
Okay, see you then.
Yes, sir, yeah.
Hello.
Okay.
Sir, Joshi ji, please wait. I think
Good evening, sir.
Negi is having some queries, yeah.
Sir, actually, my query was like there is a thrust, a Jonsar thrust and Tones thrust, which is in Himachal Pradesh and boundary of Uttarakhand. So, is there any link with this North Almora thrust?
The North Almora thrust runs slightly north of the Tones thrust and goes into Himachal.
Right, sir.
It runs slightly north of your Tones thrust.
Slightly north of the Tones thrust. So, it has no link with the Tones and that Jonsar thrust.
As far as I can see from the literature, I have not worked in that area. You will appreciate that this is such a large area that I have my serious limitations.
Right, sir. Right. It's okay.
And for that, answering your question, I am depending essentially on maps of Professor Valdia and the maps published by Geological Survey of India, those large atlas, structural atlas, the geological maps are there. I'm depending on those information.
Thank you so much, sir. Thanks.
Thank you very much. Thanks for your interest. Thank you.
Okay, sir, then.
So, we log out?
Yeah. We'll now close this online platform, sir.
Thank you very much, sir. Thank you,
Namaste.
man. Thank you. बंद कर दें अब?
हाँ सर.
चलिए ठीक है, हो या अटका नहीं नेट, कम से कम अच्छी बात है और कुछ नहीं.
राइट सर.
अटकता तो दिक्कत होती.
हाँ सर. हाँ.
अटकता तो समस्या होती. लड़कों ने कुछ नहीं पूछा.
नहीं सर.